So these are the two equations that we get from the previous paper. So how can we prove that these equations are true? So what I basically did, I looked for all the properties for f and other equations that are already been written. So if I plug in Newton's equation, F proportional to ma, then I can use m as like this equation that Einstein wrote it, Q equal ms del theta, as it is specific heat here. So what we can get, Q by S del theta, that 1 by T we get, it's already in here, that place. So we're getting F proportional to 1 by T from here. So now if we plug in Planck's constant here, so we can get the limitations for energy, like del E del T is greater than or equal h by 4 pi, and that's what we're gonna get from this Planck's equation. And if we use Einstein's equation, we directly get F proportional to E, which responds to this thing, energy exchange rate, that we discussed in the previous paper. So there goes the two things. And I was looking for the concentration of field, and concentration of field is discussed in Lorentz and Planck, the equation made by both of them, the magnetic force and moving charge. Like you can literally see the magnetic field affected by the force. So concentration of field, we get it from there. So there it goes. And if we look into Charles equation, actually both can be said here. Like, look at that. If theta is 0, v0, why the gas loses all of its volume? Because temperature goes 0, and what happens in temperature goes 0. There will be no force in there. So it goes with that equation. There is another part, 1 by T1, which is constant here in this equation. So that can describe this thing. So how everything is gonna happen, we're gonna discuss it in the next slide. Alright, now I'm gonna pause for a while. So in Bohr's equation, we see that the effect of static electric force on an electron, so that is the base of where we are thinking, what I was thinking about starting. So now we have got some properties related to the electron, like the electron's mass, the radius of the place that the electron can occupy, and the velocity of the electron. And we can shape them in different directions, like Bohr did back in his time. So now we're gonna use all these things to prepare our equation, and I'm gonna show you what I get at the end by using all of these equations. So I did a lot of calculation. I put a lot of things in and out to get into this place. Like we got the energy equivalence mass principle from the c square value, like 1 by mu naught root over mu naught epsilon naught, maybe that was the thing or something like that, which is equal to c, and there we get the c square from. So we applied the Q equal ms del theta, as it is specific heat. We applied the equation in the E by m here, and then we applied in the rest mass of the electron. That was the energy equivalent mass, and this one was the rest mass. And now we had these equations from Niels Bohr's models, and we did so many things, like Boltzmann constant came here literally, like kinetic theory, or the kinetic theory, we apply the kinetic theory here. And what we basically get at the end is this beautiful equation, like I predicted previously. That was a prediction upon observation of the cosmos, that velocity will be divided in, like volume will be divided in velocity. The more velocity the particle is going to have, the more concentrated the field will be. And that's what we get in here. The concentration of field is true after all, like the prediction is 100% accurate. So there is my constant, the constant that I generated. mu naught epsilon naught pi specific heat at for the C value, the mass equivalent energy from the mass equivalent energy equation, and specific heat for the rest value of the particle or atom or anything you consider. And this constant may change or something may happen to it, like this is Boltzmann constant. We don't know how Boltzmann constant, but we know exactly how it is gonna work for hydrogen atom, but we don't know it how it's gonna work for like electron or muon or pion boson. I don't know if it's gonna change or not, but that's the constant, my constant. Then there comes the 1 by del T and del T. So there we go. We got T from here, and where are the other T's? Where are the other T's? There is one T and there is another T. There you go. The T from there, the temperature. Like the temperature will be 1 by del T or del T. It will be calculated from this. And this T is from Boltzmann. This temperature is from energy mass equivalent equation. This T is from the rest mass of the electron. And there you go, energy exchange rate. That, like I predicted that it will be a rate of exchange of energy. There is a sign I have used there, which is a mystery I'm gonna resolve in the next paper. The next paper is so big, that's why I am right now giving all of it to you. Like I'm gonna write the next paper very soon. But here we go. All the predictions and all that I've said is now proved. Here, you can see that literally in this box. This box is the proof of all my work. All that I predicted come to a truth. What more I need to say? So I'm writing right now. I'm writing the next research paper. I'm gonna publish it very soon. I don't care if anyone takes it or not, but that's it. Now, this I have named this the theory of universal proportionality, according to like it goes with all the equations ever written in the history of physics. It will go with all the equations, and I have literally proved it. Now it is practical. It can be done in everyday work. It can be applied in anywhere. Climate prediction, cosmological bodies, or whatever you can imagine. Anything you can imagine, these equations are gonna work over it. Look at that. There is G from Newton's gravitation. There is H from Heisenberg's principle. There is mu naught, epsilon naught, Max Planck, I guess. There is specific heat, that is Einstein's specific heat. Joseph Black was also involved in this. There you go, Boltzmann here. So I've got everyone here, every single person. That's it. Thank you.